Welcome to 5-Minute Einstein. Today, I'm going to explain why soda explodes when you shake the bottle before opening it. Okay, if you're watching this video, you've probably seen this before. Yes, when half your soda ends up on the table, or floor, or on your pants in the completely wrong spot. Chances are, you shook, or dropped, the bottle right before you opened it. But why does this cause an explosion? First, let's visit a very important concept in chemistry, solubility. Remember those grow your own crystals projects that you did as a kid? Chances are, you had to dissolve salt, or sugar, or whatever in water. Take salt for example. Salt, or sodium chloride, is soluble in water. The water molecules grab the solid salt ions and separate them so that they end up floating around the solution. If you add some more salt, and more, and more, and more, eventually, no more salt will dissolve. At this point, the solution is saturated. On the molecular scale, there are so many dissolved salt ions, that the water can't hoard them all. So some of the salt ions are attaching back together, and becoming solid again. And this is happening as quickly as water is dissolving solid salt, so we don't see a difference. It's like if you and your friend both have a huge pile of cookies, and you're trying to steal each other's cookies, but you're stealing cookies as fast as your friend steals cookies from you, so the amount of cookies that both of you have stays the same. This is called equilibrium. Now, how does this relate to soda? Here's how. The reason that soda is bubbly, is because there is an excess of carbon dioxide gas dissolved, yes, dissolved, in the drink, which escapes as bubbles to give that characteristic fizzy taste. As with salt, there is only a certain equilibrium amount of carbon dioxide that can be dissolved in water under certain conditions, and soda at room temperature and pressure exceeds that amount. In other words, it is supersaturated. Now, you might be like, how can you dissolve? Well, more than you can dissolve. Here's where it gets interesting. The amount of carbon dioxide that water can dissolve depends on temperature and pressure. Soda is carbonated under high pressure and low temperature because this increases the solubility of carbon dioxide in the soda. When you increase the pressure, you force all the gas molecules closer together. With all those carbon dioxide molecules crowded together, the water is able to grab them at a faster rate. When you decrease the temperature
is the average kinetic energy of a substance, or its speed,
the carbon dioxide molecules are more sluggish, so they can't escape from the soda as quickly. Eventually, a new equilibrium is formed where there is more carbon dioxide gas dissolved in the soda than before. Now, screw the lid on tight to seal everything inside. Fun fact. Some of the dissolved carbon dioxide reacts with water to form carbonic acid, which contributes to the acidity of soda. This is also the principle behind ocean acidification, by the way, but more on that another time. Just imagining an ice-cold soda is making me thirsty. Man, I'd love to open one right now. But wait, this seemingly innocent action actually releases the pressure inside the bottle. Equilibrium has been disrupted. Remember from earlier that high pressure and low temperature increase the solubility of carbon dioxide in water. So decreasing the pressure decreases solubility. Even worse, if you haven't chilled the soda, then you're adding a temperature increase on top of that, which decreases solubility even more. That's why warm soda goes flat faster. This brings us back to the idea of supersaturation. Because there is more dissolved carbon dioxide in the soda than there should be, the net result is that carbon dioxide escapes from the soda. When you shake the soda, you speed this process up by creating lots of teeny tiny, and usually invisible, bubbles that make it really easy for the carbon dioxide to escape super quickly, because they have a starting point in which more and more molecules can join up and create a bigger and bigger bubble. The net result, lots of super crazy bubbles, and this. Thanks for watching 5-Minute Einstein, and I hope you've learned something new today.